So hello friends, today we will be discussing this question. So in this question, uh, a hoop or a ring is rolling on a horizontal plane, and a small mass A is attached here, right? Its mass is same as the mass of the ring. Both these things have the same mass. That is, I'm assuming it as m, right? Okay. So at the moment when the body A gets in the lower position, the center of the hoop moves with the velocity v naught. Actually, it is missing, right? So it is moving with the velocity v naught when the A object is at position is at the lowest position, right? So what we have to find, I think some part of this question is missing. So basically, what we have to find, I am telling you, we have to find v naught such that this body or this ring does not jump off the ground, or it does not leaves the touch with the ground, right? We have to find that critical v naught such that it does not leaves the touch with the ground. Okay, so first of all, how to do this question, and before coming to approach, let's analyze how this body is moving and how the point A or the object A is moving with the body. Right, so we will be first analyzing the motion of this body, and after that we will be coming to the approach how to solve this question. So first of all, let's analyze the motion, and this is body, this is the ring, and initially body A was at this position and it has initial velocity of v naught. So as it is and it is also given that the without it is rolling without slipping, right? Slipping, there is no slipping. So what we can infer from this is it might be rotating with omega naught, angular velocity of omega naught. So it is rolling without slipping. It means omega naught into r is equal to v naught. Why? Because the velocity of this point on the ring, on which the object is situated, in this position would be 0. So its velocity we can write as v naught minus omega naught r equal to 0. So from here we can infer that v naught equal to omega naught r. Okay, and after some time, let's say at t time equal to t, this body will be somewhere here. This body would come somewhere here, and this ring would be moving forward with the velocity, let's assume it as v, and it would be rotating with omega, right? This is ground, and this body would be situated here, and after some time it would come here, and similarly it will perform a whole circular motion in this ring. And basically, if you can observe, then this A body is performing a circular motion about this point, the center of the ring. With respect to this center of the ring, it is performing a circular motion. So it might be useful in this question somewhere in the future. So let's keep it in mind that it is performing a circular motion about the center of the ring, and let's see if it is useful somewhere. Okay, so we have analyzed the motion of this system of the ring and the object. Now let's come to the approach how to do this, right? So uh, if I assume any such position during the motion of this system, let's assume this is the position during the motion, and during this position let's assume this body is at angle theta, from vertical, and yeah, we have assumed the velocities, so we will be continuing with that. And so what we can see, if we see only the body, what we can infer from this, what are the forces acting on this body? First of all, so the forces acting on this body are, first of all, the normal force, which would be towards the center of the ring, right? And another one would be the gravitational force. It's always there, it is not going anywhere. And another one would be some frictional force, which would be tangential to this direction, but we are not interested in tangential direction, so I am ignoring that frictional force. Okay, and another one would be so yeah, these are the forces acting on it. So what we can write from this equation, this angle was theta, so this would be theta. So what we can write, n plus mg cos theta equal to, and its omega is given to us. So yeah, before writing to us, first let me explain why I'm writing this equation. So yeah, as I said, that this body is performing circular motion about this point, center of the ring. Let's say it's C. This body is performing circular motion about C. So what we can write is the circular motion equation about point C for this body, right? So I am utilizing that observation here. So about point C, it is rotating with angular velocity omega, right? And we have drawn the free body diagram of it. So we can write the circular motion equation, n plus mg cos theta equal to m omega square r, right? And also, right, at in this situation, what we can say, it is still this ring is still rotating. This yeah, this ring is still rotating without slipping on the ground, right? So the velocity of this point, let's name it as b, would be 0 again in this situation also. So what we can say is v minus omega r equal to 0. So omega r equal to v. So v equal to omega r, omega by r, right? In this situation also. So we can put omega equal to v by r. So it is equal to v square by r. N plus mg cos theta equal to mv square by r. N equal to minus mg cos theta. Now we will be analyzing this equation, and before giving any what is the approach of the further solution, we will be analyzing this equation, and let's try to guess what would be happening if this motion is continued, right? So as you can see, as this as the object A is moving upwards, work done by gravity is negative. This means its velocity will be decreasing, obviously. The velocity v of the center of the ring would be decreasing, obviously, as the work done by gravity is negative. So the energy of the system is decreasing, right? Okay, now we can, so as the the object is moving upward, the work done by gravity is negative, and theta is decreasing. As you can see, what we have assumed, theta is this angle. We have assumed theta is this angle. Here is the object A, and we have assumed the theta as this angle. Initially theta was 180. Now it is somewhere between 0 to 90, so it is decreasing. Okay, so what we can infer, and as v is decreasing and also theta is decreasing, this means n is decreasing while object moves upward. Right. So now what we have to find? We have to find is the critical velocity such that the ring does not leaves the touch with the ground, right? So what we can say this situation, this statement also like that. We have to find the critical velocity such that the ring leave just leaves the touch with the ground, right? What it means is it just leaves the touch with the ground and again comes in with the touch with the ground. So practically it does not leave the touch with the ground. Okay, so in this way we can find the critical velocity of the ring. So as we can see, so for this situation to happen, what we can say, the ring must leave the touch with the ground for the instance when the normal was minimum, right? Because after this, the normal when the normal becomes minimum, uh, after that the normal would start to increase, so it will automatically come in the contact with the ground, and before that it was in the contact with the ground, so practically it didn't leave the contact with the ground. Okay, so as you can see, where is normal zero in this situation? When will the normal, sorry, normal not zero, when is the normal minimum in this situation? So as you can see, theta, when the velocity is minimum and theta is minimum, then the normal would be minimum. So normal is minimum here, right? Because after this theta starts increasing, velocity starts increasing here as we are coming here. So uh, velocity was decreasing, theta was decreasing. So here normal would be minimum. So what we have to do is we have to find this minimum normal such that the body or the ring leaves the contact with the ground, right? So it is clear that normal would be equal to mg, right? Why? Because this normal minimum would be equal to mg. As what we can say is this normal is applied on the ring and it's some gravitational force was also there. So to leave the touch with the ground, it's both the upward force and the downward force should be equal. So normal minimum equal to mg, right? So in this condition, the body will leave the contact with the ground. So we have to equate the normal at the top position with mg. So come back to this equation. What we can say, normal minimum would be equal to when theta equal to 0, right? As this was theta, and at this position when a will come here, theta equal to 0, right? So normal minimum would be equal to mv square by r minus mg, cos 0 is 1, right? And mind it, v square is not the initial velocity. V square is the final velocity when the object is at top position here, and the object is at this position, then the velocity of this ring would be v square. Oh, sorry, v, not v square. It would be v, right? And its omega would be omega. Let's assume it. Okay. So this is our first equation. Yeah, put normal minimum equal to mg in this. So what we can find, mv square by r equal to 2 mg. And we can say v square is equal to 2 gr, right? Now what we have to do is we have to apply the work energy theorem. As the body is moving from here to here, so some work was also done by gravity. So we have to equate the work done by gravity with the change in kinetic energy to find the v square. What is v square? Okay, in terms of v naught square. Okay, so let's find. So how to write kinetic energy? So work done by gravity is equal. So it's simple. What is the work done by gravity? We have to just find the change in displacement of the center of mass of this system. So first of all, what is the center of mass? Initially, mass m was here, and this ring is of mass m, so its center of mass is here. And so center of mass of this system would be in between these 2 points, and it would be of 2m mass, right? And it would be at r/2 distance from the center of the ring. So, and finally it would be here, as the mass is here, as the final A mass is here and the center of the ring is here, so it would be here, so it is at r/2 distance here. So total displacement is equal to r. So work done by gravity is equal to 2mg into r, right? Now what is the change in kinetic energy? We have to find that. So how can we find change in kinetic energy? So kinetic energy at any instant is equal to 1/2 m m into v center mass square plus 1/2 I about center of mass into omega square, right? So this is the formula for kinetic energy at any instant for a rigid body. So we can find the initial kinetic energy. Or first of all, let's find what is this I about center of mass for this body. This is body A, object A. It is here, and this is the center of ring. This is center of mass. Okay, so we have to find I about this. I about center of mass would be moment of inertia of the ring about center of mass. That is, its moment of inertia of the ring about center was mr square. And using the parallel axis theorem, what we can write is its moment of inertia about the center of mass would be m r/2 square plus moment of inertia of object A about center of mass, that is m r/2 square, right? This distance is r/2, this distance is r/2. Yeah, so what is this coming? This is coming 3mr square by 2. Okay, so we have found the center moment of inertia about center of mass, and we have to. So what is the initial kinetic energy? 1/2 into 2m into v center of mass square. So yeah, come back to this position when the center was here and object A was here, right? So initially its velocity was v naught, it's given. And so what would be the velocity of this point, center of mass? What would be the velocity of the center of mass? So its velocity would be v naught plus omega it was rotating with omega. So its velocity would be v naught minus omega r/2, right? Yeah. So VCM initial is equal to v naught minus omega r/2. Okay, and we can write it omega naught. Omega naught was v naught by r. So it is equal to v naught by r. V naught by 2, sorry. VCMI initial. So v naught by 2 square plus 1 by 2 into 3 by 2 mr square into omega naught square, that is v naught by r square, right? So what we can write from here is v naught square by 4 plus 3 by 4 m v naught square, right? M v naught square. So this is m v naught square, right? We have to find kinetic energy final. Now it's quite simple. It is quite obvious what we have to do. What is the final velocity of center of mass? Center is here, body is here. So what is the final velocity of center of mass? You can write as final velocity of center was v, and it was rotating with omega. So final velocity of center of mass is v plus omega r by 2, right? Yes. So it is equal to, as omega was equal to v by r. So it is equal to 3v by vcm2 equal to 3v by 2, right? Yes. So 1 by 2 into 2m into 3v by 2 square plus 1 by 2 into 3m by 2 r square into v square by r square, because omega square was v by r, omega was v by r, so omega square is v square by r square. So it is equal to 9 by, so it is equal to 3mv square. So finally equating change in kinetic energy with work done by gravity. So what was the work done by gravity? Okay, so work done by gravity would be negative, as it is moving opposite to the gravity, so work done by gravity would be negative. So we have to equate this with that. Okay. Change in kinetic energy is 3mv square minus mv naught square equal to minus 2mgr. And finally put the value of v square from here, what we calculated here. Yeah, here. V square equal to 2gr. Put it here. And 6gr plus 2gr equal to v naught square. So v naught is equal to root of 8gr. So this is the final answer, and yeah, it is done. Yeah. So ending here, I hope you like the solution, and if you liked, you can give it a like, and you can also join my Telegram group, that and link is given in the description. And so yeah, that's it for today, and let's meet in some other video. Bye.